We have created several shaders now, which support alpha blended transparency, alpha clipping, depth testing and writing, shadow casting and receiving, and both the metallic and specular workflows for PBR. Today, I want to combine all of these features into a single shader, and for that, we will leverage the power of custom shader editors, which let us display the shader GUI any way we want, and run code whenever any property is changed. You'll also gain an understanding of what Unity does under the hood to display shaders such as URP lit. First, let's make some edits to the PBR shader. This will be a bit of a blitz through the stuff we learned in previous tutorials all in one go, but there's some new stuff in here too. Let's start with some new properties. Lots of them. Most of them will link directly to a shader command, except surface and cutoff, which are used in the fragment shader. But all of them use the float type, and all of them have a slightly different default value. From top to bottom we have surface, for opaque versus transparent objects, cutoff, which is the alpha testing threshold value, with a range between 0 and 1, 4 blend factors used for source and destination targets for both RGB and alpha, depth writing and depth testing, cull for showing only front, only back, or both mesh faces, and alpha to mask, which I don't think I discussed in the transparency video, but we'll see in action later. We'll explore each one in detail when we write the editor GUI script, but for the most part, we will use enums to enumerate different kinds of behaviors into integers, and these default values represent a value in those enums. So here, we say ztest equals 4, which corresponds to L equal in an enum we will see later. Technically, these properties are just values that get saved to the material, and they don't necessarily need to directly influence the shader in and of themselves. A property which isn't directly used in ShaderLab commands or in the HLSL code can still be useful in the editor GUI script when we want to enable or disable keywords based on the property value. With that in mind, let's add a few extra properties for keeping track of whether the shader should cast shadows, receive shadows, which blend function to use, whether to use alpha clipping, whether we should override the default depth writing behavior, and whether and how much to offset the default render hue by. Now we need to make some changes to every shader pass. In the universal forward pass, instead of just zwriteOn and ztestL equal, let's use our new shader properties to control not just these, but also cull, blend, and alpha to mask. Like we saw in part 3, to use a property as a parameter, we put square brackets around the property name like this. By the way, the blend keyword can accept third and fourth parameters. The first two control the blend factors for the color data, as we have seen, whereas the latter two let us blend the alpha component of the texture's stored colors. And alpha to mask, probably better known as alpha to coverage, is a technique used with MSAA, or multi-sample anti-aliasing, which we can use to improve the visual edges of alpha clipped objects. Here's a zoomed in example of what the difference looks like. We say alpha to mask off or on, and that's pretty much it. MSAA itself is a setting that you need to enable in the URP asset. The surface and cutoff values need to be added to the C buffer, and then we can add a new keyword called alpha test on to each pass, plus a keyword called receive shadows off to just the universal forward pass. This one is used inside Unity's lighting code to disable shadows entirely. In the fragment shader, right after sampling the base texture, we can branch off that new alpha test on keyword, and if it's been defined, let's discard the fragment if the base color alpha is below the cutoff threshold. Actually, the URP shader library contains a function called alpha discard that does the keyword check and the discard for us, so let's just use that so that our code looks a bit cleaner. Then, at the end of the function, instead of just returning the result of universal fragment PBR, let's use the output alpha function from the URP shader library to ensure that the correct alpha value gets output. This function needs the input alpha and what kind of surface we have, opaque or transparent, as inputs. We use the surface property to track whether a surface is transparent. For opaque alpha-tested objects with alpha to coverage disabled, we just output 1 every time, and otherwise, i.e. for transparent objects or opaques with alpha to coverage, we return the input alpha unchanged. Now we play a game of whack-a-mole and make similar changes to every other pass. For the Shadowcaster pass, just make sure the call parameters being used, the alpha test on keyword is included, the complete C buffer that we used in Universal Forward Pass and the base texture are both present, the app data and v2s structs now include the UVs, the vertex shader passes those UVs with the transform text macro, and we run alpha discard in the fragment shader after sampling the base texture. For the depth only pass, we have the call parameter, the keyword, the C buffer and the texture declaration, the UVs being declared and passed on, and we run alpha discard in the fragment shader. Same for depth normals, the call parameter, the keyword, the newly updated C buffer with those 2 extra properties, the base texture declared alongside the existing normal texture, and we already passed the UVs, so we just do alpha discard in the fragment shader, and that's all the passes done. That's almost every change we need to make to the shader, so next we can turn our attention to the editor script itself. I'll create a new folder inside Unity called Editor. In Unity, any folder with this name is special, since anything inside it will be stripped away in builds. Inside it, I'll right-click and choose Create, Scripting, Empty C# script, and name it PBR Shader GUI. This is the script which draws the GUI. Never mind UI toolkits, or even the Unity UI you all know and love. We're going back to the pre-Unity 4.6 immediate mode GUI for this. I know, it's ancient. This script inherits from Shader GUI from the Unity editor namespace, which gives us an IMGUI box to do all our work in. I'm gonna put our class inside its own namespace called shaderbasics.editor, and then I'll override a method called onGUI, which is called every time Unity draws the material inspector window. Here, we will collect shader properties, and I'll tell Unity how to draw them. And for that reason, we receive a material property list and a material editor as parameters. As a very basic example, let's just get the base color property and display it straight away. Let's use a method called findProperty, which takes in the property name and a list of properties as parameters, and returns the property itself if it's in that list. Simple. Now, when I say property name, I'm talking about the code-friendly name with the underscore in front of it, like underscore base color. We can call materialEditor.shaderProperty and pass in the property, plus a label string, which can just be base color. And finally, we ensure that any changes we make to any properties get saved back to the material by calling applyModifiedProperties. Next, we need to tell our shader to use this custom GUI script when a material gets inspected. And I promise, this is the last change to the shader file. Right at the bottom of the PBR shader file, after every pass block, but still within the main shader block, let's say custom editor, and then the full qualified name of this class, including namespaces. So in our case, that's shaderbasics.editor.pbrshaderGUI. After saving and clicking on a PBR material, we'll see our base color in all its glory. Okay, it's a bit of a step back, but this is just the start. I want to add the ability to swap between opaque and transparent and to toggle alpha clipping, essentially all the sort of stuff that you'll find under the surface options section of the URP lit shader. That's why we added all those properties to the shader after all. And while we're at it, why not implement these little drop-down sections in our own material window? After all, we have total power over the look of the GUI. Let's add a few variables for the little drop-down sections. Unity stores each of the sections inside a material header scope list, so we can create one on initialization. This type can be found in the Unity editor.rendering namespace. Then we will need to access the underlying material editor throughout this script to actually draw properties. Finally, I want to include a Boolean value to check if this is the first time onGUI is called while the material inspector is open, so that we can do some one-time setup on the first call. Just after the onGUI method, I am going to write a few empty methods, one for each section I want to have in my material inspector. I'll base my structure on the ULP Lit Shader's material GUI, so I'll have a surface options section, then PBR inputs, and lastly advanced options, so one method for each. They all accept a material as their only input. Then, in onGUI, we can create those sections. First, let's remove what we already had, and then I'll do a null check to ensure that we have access to a valid material editor, throwing an exception if it's missing. If we do, let's keep a reference to it since we'll need it later in those three methods that we just created. And then grab the material, which is that editor's target. That's the thing being inspected. Next, I want to make sure that we have a reference to each material property before trying to draw them in the inspector. Later, we will write a helper method called findProperties, which will accept the material property array as an argument. So let's pretend it already exists and call it here. Then, if this is the first time open, let's register the three methods in the material scope list by calling registerHeaderScope. It takes in a parameter of type GUI content, which we use to hold the actual text to display on the header, then a bitmask value that Unity uses to track which of the headers have been expanded and contracted, so each section uses a 1, which is bit shifted a different amount to the left. Then the final parameter is an action. This essentially lets us pass in a method as a parameter, and it's specifically an action on a material, which means that they must only accept a single material as a parameter. That's what we have, so we can just write the names of each function as the last parameter. Then, make sure we don't call this setup code on the second call to onGUI. Finally, we call drawHeaders to actually display each header section. The inspector currently looks quite empty, so let's get the surface options working. First, we need to declare some data for each of those shader properties we added. For each one, we need a lot of information. Its code-friendly name, with the underscore, its human-friendly name, an optional tooltip for extra information when you hover over the parameter in the inspector, a reference to the material property, like we had previously for the base color, and a nice extra would be the shader ID related with the property name. But this is going to look stupid and complicated if we need like a million lines of setup code, so I prefer to create a little struct to hold all this data, and then we can just call a constructor to set up each property on its own line. That struct looks a little like this. The constructor takes in the code-readable name, the human-readable label, and a tooltip description, and it auto-generates the GUI content to hold the label and the tooltip, plus it calls shader.property.id to get an internal ID based on the code-readable name. That last one isn't strictly necessary, but apparently it's more efficient to call methods like material.getFloat by passing in the integer ID rather than a name string, so we'll do that. With that setup, we can just crank out variables for each of the shader properties we added, making sure that you check the spelling of the code-readable names very carefully. Base color, base texture, use specular, metallic map, metallic amount, specular map, specular color, smoothness map, smoothness amount, convert from roughness, normal texture, normal strength, height map strength, occlusion map, occlusion strength, emission map, emission color, surface, cutoff, source blend, source blend alpha, Z right, Z test, call, alpha to mask, cast shadows, receive shadows, blend, alpha clip, Z right control, Q offset, and Q control. Can you imagine needing 5 separate variables for each of those? You might want to pause the video or peek at the GitHub repository to copy all of these into your own script. I'm now going to write that findProperties helper method. As I mentioned, it takes in the material property array as an argument, and we use findProperty to grab a reference to each one. This time, we're feeding the name member of each PBR shader property struct instance as a parameter, and setting the prop member using the result. We need to find them all here, and now every shader property is available to us for drawing once we call find properties in onGUI. Next, let's create some enums that we need for controlling the shader's behavior. The first is called surface type, which contains two settings: opaque, represented by 0, and transparent, represented by 1. You probably see what the point of the enum is now. We need a way of mapping different human-readable concepts to distinct integers which the shader and our script can use. The next is called render face, which maps front to 2, back to 1, and both to 0. This one controls which side of a face is shown. Then we have the blend function enum, containing alpha, pre-multiply, additive, and multiply. The Z-right control enum, containing auto, force enabled, and force disabled. And finally, the Q control enum, with auto and user override values. If you want the enum entries to use increasing values starting from 0, you don't actually need to specify each number value, but I think it helps to make things clearer. The order and values I've chosen for each enum reflect the values used by some of Unity's internal shader GUI scripts, so you'll have a slightly easier time following what's going on there if you ever dig into Unity's code. There's actually one last enum which we will use for the z-test comparison function, but Unity provides one called compare function, containing these values. C less equal is the fifth value down, but the list is 0 indexed, so it corresponds to the value 4, which is what we used as the default value earlier in the shader. Later, we're going to need some arrays containing the names in each of these enums, so I'll set up variables for each one, including compare function. The last variables we'll need are some strings used for keyword, tag, and pass names, as well as a variable for offsetting the render queue value, which we'll discuss in more detail when we add the advanced settings to the shader. Next, let's create a helper method for setting the blend modes, which accepts a blend function, surface type, and material as parameters. This method is responsible for setting the source and destination blend factors, which are enumerated in Unity's built-in blend mode enum. If we have an opaque object, that's easy. We just use 1 and 0 respectively, so let's use those as the default values. By the way, blend mode can be found in the Unity engine.rendering namespace, so we'll say we're using it at the top of the script. If the object is transparent, then we'll set blend factors based on the blend function we have chosen. For alpha blending, we use source alpha and 1 minus source alpha for the RGB factors, and 1 and 1 minus source alpha for the alpha factors. Then for pre-multiply blending, it's 1 and 1 minus source alpha for both sets of factors. For additive blending, we use source alpha and 1 for the RGB factors, and 1 for both of the alpha factors. And finally, for multiply blending, we use DST color and 0 for the RGB factors, and 0 and 1 for the alpha factors. Lastly, we use the setFloat method to set each value, using the shader IDs for each property and passing in the 4 factors we just set. And now, finally, we can start work on the draw surface properties method. Previously, to display the base color, we just used materialEditor.shaderProperty, because we didn't need to do anything special, so it was okay to just use the catch-all property drawing function that is shader property. Now though, I want to be a bit more explicit about how some of these properties get drawn. To draw the surface property, I'll use a different method called popUpShaderProperty, which draws an enum dropdown. It accepts the property, a GUI content, and an array of names of the enum entries. Next, I want to draw the option to choose the blend function, but I only really need to display this if the object is transparent, so we can first use the getFloat method to get the value of the surface property. If the object is transparent, then we'll display the blend property using the same popUpShaderProperty method. Let's also save the blend value into a variable for later. Next, we can use the pop-up shader property to display the cull, Z-write control, and Z-test properties, followed by the alpha clip property, which we'll need to treat differently because I want it to show up as a tick box in the inspector. There are multiple ways we can do that, but since Material Editor doesn't have a convenient method for drawing a tick box, I'm going to use an editor GUI helper method. The underlying property type is a float, which should either be 1 or 0, so we can convert it to a boolean, then use a method called editor_GUI_layout.toggle, which draws a toggleable box and returns the boolean state of that box. It accepts the GUI content for drawing a nice label and tooltip in the inspector, and the initial boolean state of the box. So the boolean value remains the same unless we click the box this frame. The annoying thing here is that we're not using a built-in material editor method, so Unity doesn't really know that this toggle is linked to the material property value, so it won't log an entry into the undo-redo system. We need to do that manually. Using a pair of methods called editor_GUI.beginChangeCheck and endChangeCheck, we can detect whether the value of that toggle changed this frame. If it did, then we can use the undo.recordObject method to insert an entry into the undo-redo stack, which saves the full state of the material to memory. Then we can change the alpha clip property on the material. Now, if we toggle alpha clip and then undo it in the Unity editor, Unity will restore the material to the same state we saved with undo.recordObject, and forget about all changes we made after calling it, namely setting the property value. If the alpha clip property is ticked, its value will be 1, so in that case, we can also display the cutoff property. We have full control over how the GUI gets drawn, so it would also be nice to indent this property a little, which we can do by incrementing editor_GUI.indentLevel, then decrementing it after drawing the property. Right now, most of these settings don't change the shader's behavior, because as I mentioned, we need to do the work of setting keywords and render modes here in the GUI script. That depends on the surface type and the blend function we chose. Let's set up some variables for the default states of alpha to mask, the render queue value, and whether we write depth. If the surface is opaque, then we can use the setBlendMode method that we wrote earlier to make the shader use 1-0 blending, and by default set Z-write to 1. We also need to disable a keyword used for transparent rendering called surfaceTypeTransparent. If alpha clipping is enabled, we need to enable the corresponding alpha_test_on keyword and use the alpha_test render queue. We also need to change the shader's render type to alpha_test with the setOverrideTag method, and finally ensure that the shader uses alpha to mask appropriately, which improves the image quality around cutoff pixels if MSAA is being used. If alpha clipping is disabled, then we disable the alpha_test_on keyword, just in case it was previously enabled. We set the render queue to geometry, and then set the render type to opaque. That's what it is by default, but it might have been changed previously. If, instead, the object is transparent, we do roughly the opposite of everything we just did. The render type should now be transparent, and the setBlendMode method will now set blend factors based on the blend function that we chose. Z-write should be disabled by default for transparent objects, the render queue should be transparent, and let's enable that transparency keyword. Depending on whether alpha clip is active, we can enable or disable the alpha_test_on keyword, but we don't need to swap render queues like we did for opaque objects. After closing out the if-else statement, we can set the alpha to mask value appropriately, and then let's deal with the Z-write control property. If we're using auto mode, then we can use the default value that we just set up. But if we're using force enabled or force disabled mode, let's override the default use Z-write value, and then set the corresponding shader property with setFloat. The shader should only use the depth only pass if depth_write is enabled, so we can use the setShaderPassEnabled method along with the pass name and a boolean value to enable or disable the pass. Next, let's think about this little section you can see on UOP's built-in shaders at the bottom of the inspector. Here, we can use a slider to change the rendering priority of an object. The effect is most easily visible on transparent objects which don't write depth. Behind the scenes, this is actually modifying the render queue value of the material by adding the priority value to it. The problem is, when we modify the surface type, we also modify the base render queue value, so we'll need to add this offset back on whenever we change the surface type. We'll worry about actually adding this priority slider a little later. With that in mind, if we're using the Auto queue control mode, this slider will be active, so we can add the offset and manually set the material's render queue value. Finally, we can write some code for the cast shadows and receive shadows tick boxes. These work much the same as the alpha clip tick box, so we'll need to do a similar thing involving editor GUI layout.toggle and a manual undo.record object. Both these tick boxes have some special behavior. For the cast shadows toggle, we'll set the shadow caster pass active or inactive, much like we did for the depth only pass. And for the receive shadows toggle, we need to enable or disable a keyword called receive shadows off based on the shader properties value. That's all for the draw surface properties method. It's a long one, but it's doing a surprising amount of heavy lifting managing the state of our shader, and adding this to our code has vastly increased the power of our shader. It's just hard to appreciate that when we can't change any of the PBR texture maps yet. So let's add all those back in the draw PBR properties method. This one is considerably shorter and simpler than draw surface properties. First, let's add back the base color and base texture properties. Instead of just using the shader property method to draw them, which is perfectly fine, we can neaten up the inspector window a little by using the texture properties single line method instead, which draws a small thumbnail image instead of the regular sized texture property icon. For some reason, this accepts the GUI content and the material property as parameters the opposite way round to the shader property method, which is slightly annoying, but oh well. The nice thing about it is that we can chain another property onto the end to draw it on the same line. So let's also throw in the base color here too. In the inspector, both the texture thumbnail and the color picker are shown on the same line. Nice! By choosing to draw the base texture like this, we have lost access to the tiling and offset options, but we can draw those back in with the texture scale offset property method, which takes in the base texture property as input. Remember that this tiling offset combo is used for all PBR textures, so we only need to add this back in for the base texture. Following this, let's add the toggle for the use specular setup property. Since we originally set up this property in the shader with a toggle attribute, we don't need to do anything weird here like we did for the alpha clip property. We can just use the shader property method, and Unity will display it as a tick box, just like we want. Depending on the value of that property, which we can get directly from the material property with the ints value member, we'll display either the specular map and specular color, or the metallic map and the metallic slider value. And then after that, we can simply display each of the PBR maps using the texture property single line method to display their respective additional properties, and convert from roughness can use the shader property method. Told you, shorter than draw surface properties. The only thing that's left to do is to fill out the draw advanced properties method. This one is also relatively easy. First, let's display the queue control enum property. There are only two possible values. If it's set to auto, then we want to use the appropriate render queue for the type of surface that we have, opaque, alpha clip, or transparent, and then add an offset. We can handle the actual logic for setting those values back in draw surface properties, but we display the slider here. We can use a method called intSliderShader property, which takes in minimum and maximum possible values as additional inputs. Unity's built-in shaders use -50 to +50, but you can change that if you'd like. If the queue control is set to user override, then we want to give the user complete control over the specific queue value. There's actually a handy render queue field method for doing this, and it appears like this when viewed in the inspector. And that is essentially it. We've now created a much nicer inspector window than the default one Unity gives our materials, and we have vastly improved the feature set of the shader. It's much more flexible than it otherwise would be, as we can seamlessly swap between an opaque and transparent surface, choose which sides of each face to draw, control how the depth test is performed, choose whether to clip based on an alpha threshold, and both cast or receive shadows on a per material basis. We also have total control over each PBR map, of course, and over the render queue of the material, so we can intentionally draw some objects over others in a strange order, especially if they use the transparent render queue. That was a beefy tutorial for such a seemingly simple topic. Until next time, have fun making shaders.